Okay, my friends, this is going to be great. They're looking for neutrinos. Now, this is the world's biggest water tank. They're hollowing out a mountain in Japan. And they've been doing this for 20 years. And this huge, huge, huge expanse, they're going to look for the tiniest particles that exist. They want to find neutrinos. Now, listen to this. Our universe is made up of tiny subatomic particles. Subatomic means smaller than an atom, tinier, that's tiniest. They call them quarks, bosons, and the smallest of them all are neutrinos. All right, the smallest of all the particles are neutrinos. Neutrinos act in strange ways. Now listen to this statement, and I'm going to explain to you why it makes no sense whatsoever. Neutrinos fly through space, but don't interact with other matter. They don't interact. Billions of them move through your body all the time without having any effect on anything on you at all. No effect whatsoever. And they move through space with no effect whatsoever. How did they know they're there if there's no effect on anything? It's the most ridiculous statement I've ever heard. It says if we understood how that happens, it could fundamentally change how we think about the universe. Neutrinos are the smallest building blocks, and I will show you them. We have discovered them. They are doing all this work, spending billions and billions and billions of dollars to try to find these neutrinos. And look at the size of this thing they had built. I'm going to show you neutrinos right now. We could create them all day long. All right, let's start with what neutrinos are. They're looking for the bits and pieces that make up protons and neutrons. All right, when they smash together, they get all these bits and pieces, and they search through them to see if they can keep seeing over and over and over the same tiniest particles that exist, and they do. And they are called muon neutrinos and electron neutrinos, and they have seen them. Now, they're trying to isolate them to see them specifically in this chamber. And so they started on that, like I say, 20 years ago. A lot of things have changed since then because we can see them now easily. The whole problem is that protons and neutrons are not just big solid things made of a few quarks and a couple other little things. No. They're 1823 or so for a proton and 1824, an even number, for a neutron. The proton is a bit of a charged particle. All right, it's got, you would consider to have a positive charge, but it could go either way. But it's going to be a charged particle. Now the neutron is going to have an even number, so it doesn't want to take any more on or give any up. A proton has an uneven number, so it might want to take another one on, or it might want to give up one of these particles to get to an even number. But when it has an even number, it's a neutron. Think of it that way. When they smash together, and they're the smallest stable quantities, except for a photon. That's a photon. All right, they see them. And they see these particles, these tiny little particles, and they know they're there. But it's just in a pile of debris, so they don't know where they came from. They just know that there's a bunch of them there. Now they want to try to isolate how they form, what they look like, and all that. And I can show you how they form and what they look like right now. So let's do that. Don't forget, when they smash together, they just get in debris. When we smash our particles together, we started with light. So we started down in this realm right down in here. All right, we didn't have to do this big smashing bits and pieces. All right, so this is it right here. This is a Dirac neutrino. It's got the white and the black. Very clear. The Majorna neutrinos are like, they're not quite fully formed. And this is what I see in photons. This is what I see in neutrinos that are becoming photons. But that is the signature in my world of a true photon. And I'll show you why I say that. All right, my friends, I'm going to make this simple. It can be really difficult to understand, or it can be simple to understand. I go with simple. The only two particles that exist is a white, glowy, charged, energetic particle, which is half of the neutrino, and the other half is the dark muon portion of the neutrino. Together, they make a gluon, which is the tightest particle you could ever make. You can hardly pull these apart. However, we devised a way of forcing the white to leave itself from the black, because the white can get big and it can get almost down to nothing. The black never changes. That's a fixed particle, never changes. It stays that same size. And that, my friends, is dark matter, and it creates gravity. Because everything there is has that particle attached to the white ones. Everything there is made of dipoles. It's called Dipole Electron Flood theory. All right, Dipole Electron Flood theory. And this is what a proton actually looks like. The dark matter, remember I showed you in the Fermi neutrinos, there's a dark and a white. And there's 1,823. Those are the smallest particles that exist. And there's approximately 1,823 of those. Each one is like a little bar magnet, and they glob together to form a proton. 1,823, not one with a couple of quarks. This is 1,823 dipoles. Now, in the subatomic realm, unlike bar magnets, these can push to the center. The dark particles, the black particles, go right into the center, and they are surrounded completely by white ones. That's why we've never seen the dark particles ever. This is dark matter. You can't see it. It doesn't reflect. It doesn't absorb. It doesn't emit. And all it does is collect the white around it. And the white so desperately wants to be attached to that black. That's called a strong nuclear force. That's nuclear gravity. That's subatomic gravity, where all these particles collect around the dark. The dark matter is gravity. It's dark matter, and it's all the weight. These have no weight whatsoever. The only thing I can come up with to account for the reaction of these particles is they have literally no weight to speak of, zero, basically. So they have no weight, but they have a hell of a lot of energy. What could cause that? The only thing I can think of is they, instead of being a solid like this, these would be some kind of like soap bubbles, a very, very thin soap bubble. And when you bash into it, it does that kind of stuff. And I said, no other thing I can account for. But they don't move. They don't have a whole lot of interaction. They're not pushy. These are the pushers. Those push things. These are, all they care about is being attached to that. They'll try to get back to that. That's what electricity is. These are separated and then coming back to that black. That's what electricity is. And I'll show you, we actually have created subatomic nuclear explosions. I'll show you. Okay, my friends, let me just explain to you what they are looking for, which is the tiniest particles that exist. However, they're using huge particles, and they're coming together, boom, like this, and then they see all of this debris come flying apart from this collision. Now, what they are seeing is two of these things coming together, hitting head on, and instead they're seeing little bits and pieces go flying here, and chunks go over there, and one go over here, and two go over there, and they're just everywhere. But they have this tendency to spin. These particles spin, and I think I might have discovered why. And I'll show it to you. But this is what they consider to be a Higgs event. Now, let me show you our Higgs event. Okay, right here you can see that light can accelerate. There's no question whatsoever that light is accelerating. You know what? Oh boy. Okay, here's where we start right off. We have a problem with mainstream science. Photons, they say, are the smallest possible particles of electromagnetic energy. Therefore, also the smallest possible particles of light. So these, they say, photons, which is light, are the smallest particles that exist. Photons can travel at the speed of light because they have no mass. Well, that's not true. Thanks to relativity. No. Thanks to relativity, everything's wrong. Photons have no charge. That's not necessarily true either. They are neutral, but they are not, they do have charges in them. Photons represent the entire spectrum of electromagnetic radiation. Correct. All of the photons can be sound waves. All right, all they are is particles. Photons are, I will show you what photons are, because we actually photoed the photons. All right, and I can show you they're nothing that they're thinking. All right, here's a this is strictly pulsed red laser. Now remember that statement. Photons are the smallest particles that exist. Right? That's what it said. They're the smallest particles, and there are light. Light is light. I don't care if it's laser light, or it's candle light, or if it's sunlight. It doesn't matter. That's light. Now, it does have a magnetic field around it, and it is also a particle, and that's what creates the wave. And the particle, it has the field around it, so that creates the particle. So the particle has the wave, it pushes through all the other particles. They have to glow, because anytime you push a particle against another particle, it creates a glow. It creates energy. And that's what this is. It's starting to get energetic because we are accelerating that into a Venturi. You wouldn't even see this if it wasn't starting to accelerate. The only reason you're seeing it right now is because it's in the acceleration phase. And now I'm going to show you full acceleration is right here. We were looking at this right about there with nothing ahead of it, remember? Let's make sure you understand this. This is a little tricky, but you got to look at things carefully. We were right here. We had pulse, 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 and we were right there. All right, we're now approaching a Venturi, sucking that particle right out. But here's where we were just a second ago. Right there. It's just getting ready to accelerate. By here, it's going to be taken off like a rocket ship. So there's the beginning pulses. All right, and here is what happens as it gets close enough to the Venturi to be sucked forward. This is suction, literally suction. Right out of there. All right, so it's coming here, it's coming here. You can see it's sucking itself right out. This is just, it's like accelerating so fast, the particle, that it's pulling itself out of its own magnetic wave. That's just like breaking the speed of sound with a jet fighter. Well, that's breaking the speed of light. We're way, way ahead of the speed of light. Now, what happened here? What happened here? And why is all this white stuff? What's going on with this? And where do these things come from? Where do they come from? I don't see them back here. I see this one coming, but I don't see these. But all of a sudden they show up. Now I can explain to you exactly why. And it's because of the reverse neutrinos, which is the white neutrinos, which are the electron neutrinos, are coming back so violently that the waves that are here, that normally you would never see them, they are glowing like crazy. They're leading edge because of the reverse electromagnetic field. All right, and down here is where you can see it's still wave, wave, wave. This is a subatomic nuclear explosion, and so is the ones they're doing at CERN. When they hit these head-on colliders, all right, it's a subatomic nuclear explosion. When I say subatomic, what does that mean? It means these are protons. These are atomic particles. You break these apart, it's subatomic particles. So when they're coming here as atomic particles, they explode. Well, what is a subatomic explosion? It's a nuclear explosion because these are parts of the nucleus. It's a nuclear subatomic explosion. That's what they're doing when they hit their head-on colliders, exactly what we are doing. But we're doing it more efficiently and much more elegantly, to be perfectly honest with you. And it ain't bragging if it's true, and it's true. Because all we did, instead of trying to hit them head on, very, very difficult, because they got this big bubble field around them. They go boing, to boing, to boing. Every now and then you'll get one that'll hit, but very, very, very rare. Every one of ours hits. Right through there. And if we had a whole batch of Venturis here, all down the line, all of these would, I would think, they'd do the same thing. They'd all create this white spray. So you'd have a whole line of white spray coming through, and that white spray is electricity. That's the stuff you want to put in your car and your batteries and run your car, run your house, and everything. That's the product of electrical generation. And electrical generation is, you have dipoles, you have the electrical negative part, which is the white, and you have the positive part, and you have to rip those apart. And when you turn on a generator, if you know how generators work, and you have one, you plug everything in, you get ready to go, and when you turn it on, it goes and what it's doing is it's ripping and ripping and ripping and ripping the particles apart and forcing the white ones to be collected into a your circuits in your house, basically, when you do a generator. But when you do a battery charger, same thing. It's charging by separating the white and putting the white in the batteries. And when you put that white in your batteries, there is no increase in weight whatsoever. The batteries do not increase in weight. I mean, it could be some nanograms of weight that they increase, because there's got to be something. This is what's killing me. There's got to be something. But all I can figure now is that the black particle, which well, maybe I didn't show you. Hold on. Here's the particles. Well, remember the light. Here's the light coming through. This is the particle right here now. It's gaining energy, gaining energy, gaining energy. Right here is full-fledged photon when you see it white. Whenever you see them white, it's just like it's bouncing back at you. It's a photon. Up to here, it's a neutrino. Now let me show you that actually happening. What we're going to be seeing now is this event as it's turning into that event right there. And we're going to be seeing it right up to about there. So it's probably going to be about from there to there. So the neutrino grows in energy, 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 and then it goes really into a photon phase. Right there is the photon phase. And here's what it looks like as it's doing that. All right, let me turn this light on. All right, this is the the neutrino phase. And they're just not pumped up enough to be fully photons. So, and they could say they change flavors. Yeah, they get more and more energy, that's all. They turn sideways here, like a Oreo cookie, and then they go sideways this way. But the ones directly in line it feels like it hit a stone wall here. That's why it's bouncing back real brightly here. Coming up, you don't really see them really bright. They get brighter and brighter as they come up, yes. Over here, there's light particles all over here. They're all over here and they're all down below, and you don't see them. They're starting to show up here because they're starting to gain energy as neutrinos. But the only time they show up as a full-fledged photon, it appears to me, is just before they hit the Venturi, because they think they're hitting a wall. Let me just explain it to you. Take your time and think about this. Up here, these light particles are up here too. It's the same as this one here. The only reason we see this is because it's being pulled forward because of the Venturi, just this particular one. They're here, they're here, they're here, they're here, they're all over the place. But you don't see them because they're not being accelerated or pushed back on. Now, the particle here, we don't really see it yet. And here it's kind of dim and a little dim. It's getting brighter and brighter and brighter and brighter and brighter. And here it starts to show as a white particle. And the reason it does that is it thinks it just hit against a wall where it would bounce back at you. Because this is all bouncing back so hard, making these things also. These are nothing more than the tips of photons. And they're being pushed back at so hard that they just turn on like a spotlight. You see that? That is serious action. And here you get your electron showers, and the black particles cannot get through. So here we have fission and we have fusion when they come back together. Let's look at that real careful, because don't forget, I'm claiming that light accelerates quite easily. The neutrinos show as they gain value, and then they turn into photons as they feel like they're concussing against something where they would bounce back at you, and they are bouncing back. They are emitting light backwards at this point. That's what, and again, let's just look at it again. All right, here they come. Up here, we're not seeing anything, but they're the same as they are here. They're all over here. It's the only one we see, though, is one that's going to bounce back at us. And it is. You see that white bounce back? This thing thinks it just hit a wall. It says, and that's what we see when it bounces back. We see these coming back, and however hard it hits and what it hits against determines how fast it's going to bounce back at you. That determines the color, which is the spectrum. And we only have this right here, is that little tiny bit of the spectrum. It goes way up, and then there's a ultraviolet catastrophe, and it changes into just nothing more than the black particles. The white ones are gone. After the ultraviolet catastrophe, the white ones are gone. And then from then on, it's only the black particles, and those will kill you. And then below this, infrared and microwaves and so forth, those are vibrational frequencies. They, infrared and microwaves, your microwave shakes water, boils the water and so forth. Radio waves, you can hear them in sound and so forth. And anyway, this pretty much shows you what a photon is. This is from light. There's no question what it is. Who can question this? And I would like to have somebody question and say, no, Roger. And they did. They said, no, you're an idiot, stay away. There was no questions. I've never had a question yet, not one, zero. I'm showing you, start out with this, and this is the beginning tip of the wave. It's just beginning to accelerate, and we would not see that were it not for the acceleration. We wouldn't see that. It would be just like all the rest of the stuff. It would just be a little bit of a glow in the air. You wouldn't see that wave. And the only reason you see these waves here is because it's being pushed back at instead of being pulled forward. Same effect. It's pushing, they're shoving back, it's glowing. This one's just sucking forward, and that's why it's glowing. But it doesn't glow much way out here. But it's quite obvious what it's doing. And again, subatomic nuclear explosion, fission, fusion. Now let's see the fission and the fusion and the neutrinos. And this is not my pictures. This is from CERN. All right, you see this right here? This is what they want to do. All right, Cherenkov radiation is a decay type of radiation. And what they do is they send in high energy, very high energy particles into heavy water. And the muon separates from the electrons, and the electron neutrinos, and they turn into showers. So they see the muon go on its way. It's called a sterile muon. And they see the electron neutrino turn into showers. This is where you get all your energy. All right? It produces an electron neutrino event, produces multiple cones, and therefore a diffuse ring in the detector array. Now they're just detecting these. And that's what this whole thing is, this gigantic cavity they're building. Well, we have them right here. This is them. All right, the black ones are the muon neutrinos. They separate. Now they're hitting heavy water to, make them force them apart, because one of them is heavy and one of them is light. Well, we're hitting the Venturi, which will only allow the white to get through. And nothing but white there, zero black. The black ones stay away. Now, the other thing to take away from this, to understand, is the black is on top of the white. You see it? Every one of those balls is the same size. They're exactly the same size. Every single one of them. You see them as a little different sizes because they're wrapped around with the white, or they're just way ahead of the white. Like this is about the biggest one you're going to see. But they're all the same if you could actually measure them with a caliper. Because there's one size fits all. And the red and the green, just to make sure there is no difference. It's just one goes fast and one goes slow. All right, there's the same particles. And it's nothing more than photons. And here's the neutrino phases. Same as we had before. Same particle, it's just it's spinning faster. And when you say spinning, I say, yes, spinning. And you say, show me the spin. Like, yeah, I'll show you the spin. Here it is right here. What happens with particles of light? Hold on. My little speaker on here. All right, you ready? Here's what's going on. There's the particle of light in the front here. And it is spinning like this. That's what these do. They spin. So that real particle spins through that slit. It has to crush all its fields down into that slit. And then when it comes out the other side, they stay away from each other. These are repulsion patterns. This is a single slit. Single slit. It has nothing to do with double slit. That's all nonsense with waves and flapping. Light spins. And I can show you when it comes back together, when it separates the, excuse me, the black and the white, when it comes back together, I think I can actually see it take off and start spinning. And those are the Higgs fields. They have the Higgs fields backwards. They say a Higgs field decays into other things. No, a Higgs field is when the decayed particles come back together. That's what a Higgs field is, and I'll show you right now the Higgs fields. And I'll show you, I think I can see them actually beginning to spin. All right, so here we are separating the particles. The black ones can't get through, only the white. And there's a tiny, tiny, tiny little slit here. And the white can squish down and get through, and the black can't. The black is a fixed size, same size. And the only reason we're seeing them is because they're sitting on top of the white. They're all over in here. You just can't see them. You could just barely see them as they kick into the white. And they want to be attached to that white. They want to be attached desperately. They will never stay apart for more than a bazillionth of an inch. And this is the speed of light, so that's pretty fast. They're coming back together, which is fission. And back together is fusion. No other way to look at that. We're not using heavy particles. We're using the base particles. The smallest particles that exist, light. You saw what they say. They're the smallest bits of particles. But we actually separated the light from its own self. All right, if you look up Higgs fields, they see these swirling patterns all around, and they call them Higgs fields. Well, we see them too. Now, what they don't realize is, though, that these Higgs fields are when these particles are coming back together, not when they're breaking apart. They think that when they see these Higgs fields, they're falling apart. That's my interpretation of what they're saying. And I say no, that's when they see them coming back together. Because here's where we separated the white from the black. You saw there was no question whatsoever. Zero question that we separated the white from the black. Well, and there's also zero question that the white wanted to be back to the black. And that's this event happening right now. Now, how can I prove this? I really can't, but I can show you. I think I have evidence that supports what I'm saying. These white particles want desperately to be attached to black particles, and there's just a soup of black. So they just instantaneously start to spin these black particles for some reason, and I can't tell you why. But this is the key. Look at this one. This one here is all by itself. Now let's look at that real careful. You can see some of the black coming into them. The black wants to grab into them fast, and these are ones that are starting to spin along. If you look real carefully, you can see the black is in with them. There's little black particles that are starting to seep into them. Now this one was the cool one. It's a white particle coming out, and then you see a little black starting to kick in, black, and now up here you see black, 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 and then it's just, it doesn't keep going forward. It just takes off in this spin. Now what makes it spin? I have no idea. I just really have no idea. No idea, but they seem to do that in a regular pattern way. I mean, I have pictures of these just coming out of my ears. And as they get further and further out, they get more and more stretched, and then they just sort of go back into the background of gases and so forth as particles. I don't know. Light particles, really. Because if you think about this carefully. What did we start with? What did we start with before we separated that particle? We started with these. All right, think about it carefully. We started with these. Then we broke these apart, and now they're coming back together. Let's think about this rationally. Okay, this is rational thinking. Here's what we started with this. That's the same as what I just showed you, Higgs fields, basically. But that's light. That's before it was accelerated. That is the leading tip of a pulse red laser construction laser. All right, and this was taken with CMOS, which is exactly what they use now at CERN to see their experiments. They upgraded to use CMOS. We were doing this in 2014, 2015, Rod Warren and I, and this is CMOS. So, and you can see the result. We can see these particles, and we're not interfering with anything. All we're picking up is the radiation. So it's just going to go past us so there's no observer effect. Before, and I went to the University of Geneva for particle physics to try to explain to them what we were doing. And I did. And they listened. And we talked. And I said, these are particles. And I showed them the particles. And I said, I showed them the whole thing that I'm showing you. And they didn't disagree. But apparently they just thought there was something different between the nucleus being particles and a nucleus being one big glob of who knows what. Because they got a particle zoo. I think I showed you that. Maybe I didn't. Hold on. This is what they get, the particle zoo. And what is the particle zoo? For us, all we started with was this. We never get any bigger than that. They started with gigantic globs of these, smashing them together. So now an X particle is a chunk like this. Plus, that's basically a little radioactive. These, because it's not a proton or a neutron, it's a portion of a proton or a neutron, and that wants to become stable. That makes it a little radioactive. I'm surprised. I got to look up to see if they have been checking for radioactivity. I would imagine they would, but who knows. But the rest of it, they're going to dig around and try to find these tiny little particles. And we started with the tiniest of the tiny particles, which is light. So we didn't have to dig through anything. And this is what they see is all this stuff. And I'm telling you, some of these chunks, I think these could be a little dangerous. I got to look into that. Yep, just as I expected. Large radiation protection at the Large Hadron Collider. All right, yeah, it's challenging, it sounds like. The primary beam and secondary particle showers, which is these huge particles smashing together, they form all those chunks, produce a prompt, instantaneous, and a residual radiation field that pose unique radiation protection challenges. So they're just breaking these pieces into chunks. We never have any bigger than this. You can't get any bigger than what we started with. So I believe we have no issues with radiation. Okay, I don't see any reason to go any further on this. I think I have made my point very, very clearly. And these are the Fermilab says these are the neutrinos, and they are the smallest particles that exist, and I show them in their phases versus their completeness, which are in the photon phase, and I show everything. If I haven't shown you, and again, these are not my words. Electron neutrino turns into showers. Yes, exactly. The white particle turns into showers. The black particle, the muon neutrino, turns into a black muon all by itself. Yes. I love you all. I think I made my case, and I think we should be looking at this because I think we can get free energy right there. Electron showers are just scads of energy. All right, so I love you all. Hope for the best. Thank you. Bye.